Today you're very fortunate because we are not going to just solve one differential equation, not two, but three. And they all look very similar to this one right here. This is a second order differential equation. It's homogeneous and it's linear. And further, it has constant coefficients. So all three of these have these properties. Now, I want to start off solving this one by just assuming a solution to be y equals e to the mx. Let's just assume that to begin with. Now, let's see where this takes us. Well, the first derivative then would be e m to the mx. And the second derivative would be m squared e to the mx. Now, what I want to do is I want to plug back in. I want to plug in the second derivative into the y double prime, first derivative into the y prime, and the y into the y. So let's see what happens when we do this. When we do this, we're going to get 3m squared e to the mx minus 7m e to the mx. And then finally, plus 2e to the mx equals 0. Now, I'm going to factor out the e to the mx because I notice I've got one in all three of these terms. So let me factor that out. E to the mx. And now I've got 3m squared minus 7m plus 2. Now, notice that, so it looks like what it amounts to is I've got to figure out what value for m will make this thing 0. Now, I don't need to consider this. This is not going to be 0. This is e to the mx. So what I need to focus on is just this right here. In other words, what I've got now is I've got 3m squared minus 7m plus 2 equals 0. And notice this looks an awful lot like the original differential equation. But instead of y double prime, I've got m squared. Instead of y prime, I've got m. And instead of y, I just don't have the y there. But this looks a lot like this original equation. And we call this the auxiliary. So this right here is called the auxiliary equation. And this is what we're going to use to find the values for m. So now I just need to solve this, and you can use the quadratic formula, or you can factor this. I've made this one so it will factor. But you don't have to, you can always use the quadratic. So let's see here. I've got 3m and m, and maybe a minus 2 here and a minus 1 there. Let's see here. I think that'll work. So notice what we get. We get m is equal to 1/3, or m is equal to 2. So notice that gives us two solutions. So here's what we have. We have the y, I'll call it y1, is equal to e to the 1/3 x. And y2 is equal to e to the 2x. Either one of those would be a solution to this. And likewise, we could say, okay, putting those together, we have c1 e to the 1/3 x plus c2 e to the 2x. And there we have a solution for our differential equation. Now notice that e to the 1/3 x and e to the 2x, we could put those into the Wronskian and find out that these form a fundamental set. Okay, so there's our solution right there. Now, I want to, so notice the steps that we went through. We just set up the auxiliary equation and we found our values for m, and there you have it. Now I want to go to this next one. Okay, we've got 4y double prime plus 4y prime plus y. Now let's see what we get. I'm going to set up my auxiliary equation. Okay, so this is 4m squared plus 4m plus 1 equals 0. I want to solve this one. Okay, so now if I factor this one, I guess what I'm going to get is 2m plus 1. 2m, I guess it's, so what I get is 2m plus 1, and that's it, right? So it looks like I've got this solution to be m equals negative 1/2. So here's a solution that I get. I get e equals negative 1/2 x. There's a solution right there. Now, I need another solution. And this method only gave me 1. However, remember, we know how to find another solution because recently we went through this process of reduction of order. And we came up with a formula that if you want to find the second solution, take the first solution and then multiply it. So here's the first solution, and then multiply it by this. Take the first solution squared down here, and then e to the negative p dx. So there's a way that we can find the second solution. Okay, so let's use that. Let's take this differential equation up here. I've got, let me divide through by 4. So what I get is I get y double prime plus y prime plus 1/4 y equals 0. So it looks like putting it into this formula, let's see what I would get. I get my first solution, y to the negative 1/2 x. There's my first solution. And then down here, this is going to be my first solution squared. So this is e to the negative x, right? And up here, I've got e to the negative x as well. And then dx. Well, that means that my second solution is just, now notice this right here, this is just the integral of dx, which is just x. So here's what I get. I get x e to the negative 1/2 x. Yeah. So here's my solution there, and here's my, combining the two solutions, I've got c1 e to the negative 1/2 x plus c2 x e to the negative 1/2 x. And there you have it. Now notice, this is what you do when you have a repeated solution like this. Okay. In other words, doing this method, I was only able to get one solution out. So I can go back and find the other solution this way. But you don't have to go through this process every time. If you've got one solution, okay, so let's suppose you've got one solution, okay, e to the mx. Then the next solution, or the next part of this, is going to be x e to the mx. Okay? So you just put an x in front of it. Okay? Now, let's look at this one. Okay? Now, what I'm going to do is I'm going to solve this with the quadratic formula. Okay? So I'm going to set up my auxiliary equation. Okay, so here we go. Here goes the auxiliary. M squared plus 4m plus 5 equals 0. And I'm going to set up my quadratic. So I've got negative 4 plus or minus the square root of 4 squared minus 4 times 1 times 5. all over 2 times 1. Okay? So let's see what this is. This is negative 4 plus or minus, here we go, 16 minus 20 over 2. And that will give us negative 4 plus or minus, 2i, right? See, 16 minus 20 is negative 4. Square root then is going to be 2i. So here's what I get. I get that m is equal to negative 2 plus or minus I. There it is. Okay. So here's what I get. I get y equals e to the negative 2 plus I. And I get another solution, okay, which is e to the negative 2 minus I. Okay. Now, I'm not going to stop here because I want to show you a different form of the solution here. So let's recall, let's just work with this a minute. This is e to the negative 2. Oh, I left off the x. Sorry about that. Let's put the x on there. This is negative 2x e to the ix. And this one over here is e to the negative 2x e to the negative ix. Okay? Okay, so this is what we have. Now, recall that e to the pi I, or e to the theta I, this is something you've seen before. E to the theta I is equal to cosine theta plus I sine theta. And you can derive this formula through Maclaurin series. Okay? But right now, let's just take this as a given. Okay? That's a given. Now, also, note this, that e to the negative theta I is going to be cosine theta minus I sine theta. Okay? And the reason for that is that the cosine of negative theta is equal to cosine theta because it's an even function. And the sine of negative theta is equal to negative sine theta because it's an odd function. Okay? So let's see what we've got here. We've got y1 is equal to e to the negative 2x. And then this right here is going to be cosine x plus I sine x. Likewise, y2 is going to be e to the negative 2x times cosine x minus I sine x. Yeah, look at that. Okay? So now we have this way of looking at it. Now, I want to do this. I want to look at the solution. Okay. I want to look at C1, or let's see. I guess I haven't used C1 yet. Okay. So let's look at this. Let's suppose we've got C1, e to the negative 2x cosine x plus I sine x. Okay. Plus C2, e to the negative 2x cosine x minus I sine x. Okay. So we've got these two. Now, I want to combine some values here. So look, I'm going to clear parentheses, and I want to put the real parts together, the imaginary parts together. So I've got this. Notice I've got C1 plus C2 e to the negative 2x cosine x. Okay, so what I've done here is I've cleared my parentheses, and I've factored out an e to the negative 2x cosine x. So you can look and see I've got this and this, and I factored out the e to the, well, I factored out the e to the negative 2x cosine x. Okay, now I want to do the same thing for the imaginary part. So I've got C1i plus C2i. Okay, and this is going to be e to the negative 2x sine x. And actually, that's going to be a minus, isn't it? Okay, there's a minus right there. Okay. Now you notice that this right here is just one big fat constant. And this right here is another constant. So let me call this C3 and this one C4. So here's my solution right here. I've got C3 e to the negative 2x cosine x. Over here, I've got C4 e to the negative 2x sine 2x. I mean sine x, sorry about that. So this is the solution for that thing. Now, so look, I want to summarize everything. So this is the way, this is a good way to express the solution. So let me just look at a general differential equation here. Okay, like we looked at. Okay, so okay, now notice that, so I could set up the auxiliary equation. Okay, and then I set up y equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Okay, now I want to look at this part, b squared minus 4ac. If that is greater than 0, then our solution looks like this. Y equals C1 e to the m1x plus C2 e to the m2x. Okay, that's what our solution is going to look like. Now, let's suppose that b squared minus 4ac is equal to 0. Then our solution is going to look like this. C1 e to the m1x plus C2 x e to the m1x. There's what it's going to look like. Okay. Now, let's suppose that b squared minus 4ac is less than 0. That means that we have this situation. We have y equals, I'll call this y1. We have e, and let's suppose we've got alpha plus beta I. Okay? In other words, x. Let's put an x up here. Let's suppose that's what we get, and we get y2 is equal to e to the alpha minus beta I x. Okay? Let's suppose that this is what we get. Now, we go through and, we could work through generally, the same process I did here. But, and I guess I'll do that. But notice what we would get. We would get y equals e to the alpha, and then this would be cosine beta x plus I sine Whoops. Okay. Okay. Plus, and let me put a constant here, C1. Over here is C2, and we get e to the alpha, and then this would be cosine beta x minus I sine beta x. Okay. There's what we got. And you can go back and kind of fill in the gaps here if there's some gaps. Then we split this up. Okay, there's that. Plus oh, I needed to put the i's in there. And then this is going to be e to the alpha sine beta x. Okay. Then this is a constant. I'll call it C3. This is a constant. I'll call C4. And now look what we have for our solution. We have C3 e to the alpha cosine beta x plus C4 e to the alpha sine beta x. And this is the solution for when we get solutions with imaginary parts. Okay, so that's the way you solve these differential equations. Now remember, these are linear. They're homogeneous linear equations with constant coefficients. We get the auxiliary equation, solve the auxiliary equation for m, and then we go back and deal with whatever solutions we're blessed with. We might have two distinct solutions. We might have a solution that's repeated, like in the case of this one, or we might have complex solutions. Either way, this is how you deal with those.